Hello everyone, welcome back to the channel Simple GAN, where complex engineering concepts are made simple, visual, and practical. Have you ever wondered backhand index pointing right why a shaft twists instead of bending? Backhand index pointing right how power is transmitted in gearboxes? Backhand index pointing right or why shafts sometimes fail even when stress looks small? The answer lies in torsion. In today's video, we will completely understand torsion of circular shafts, from basic concepts to important formulas, from stress distribution to real industrial applications. By the end of this video, you will clearly understand how shafts behave under twisting and why circular shafts are preferred in machines. So let's begin. Torsion is the twisting of a member due to an applied torque. When a shaft is subjected to torque, it experiences shear stress and the material twists along its length. Simple definition: torsion is the resistance offered by a shaft against twisting. Examples from real life: motor shafts, gearbox input and output shafts, propeller shafts in vehicles, crane drums, turbine shafts. Whenever power is transmitted by rotation, torsion is always present. Torque is the turning moment that causes rotation. Torque equals force times radius. Symbolically, T equals F times R, units, Newton meter or Nmm in machine design. Higher the torque, greater will be the twisting effect on the shaft. This is a very important question. Circular shafts are preferred because stress distribution is uniform, no stress concentration at corners, easy to manufacture, higher strength per unit weight, better resistance to torsion. That's why non-circular shafts are rarely used for torsion. To understand torsion mathematically, we assume shaft material is homogeneous and isotropic. Shaft is circular and straight. Stress is within an elastic limit. Plane sections remain plane after twisting. Twist is uniform along the length. These assumptions help us derive simple and accurate formulas. When torque is applied, maximum shear stress occurs at outer surface, zero shear stress at the center. This means stress increases linearly from center to outer radius. Shear stress formula: tau equals T times R/J, where tau equals shear stress, T equals applied torque, R equals radius at which stress is calculated, J equals polar moment of inertia. For a solid circular shaft, J equals pi times D/32. For a hollow circular shaft, J equals pi times/32, where D equals outer diameter, D equals inner diameter. Higher J means heavy checkmark lower shear stress, heavy checkmark higher torsional strength. This is why hollow shafts are often used. They give high strength with less weight. Angle of twist tells us how much the shaft rotates under torque. Formula: theta equals T times L/, where theta equals angle of twist, L equals length of shaft, G equals modulus of rigidity. If angle of twist is too large, crossmark misalignment occurs, crossmark vibration increases, crossmark shaft may fail prematurely. So stiffness is equally important as strength. The fundamental torsion equation is T/J equals tau/R equals G theta/L. This single equation connects torque, shear stress, angle of twist, shaft geometry, material property. This equation is the heart of torsion theory. Solid shaft, strong, simple, heavier, less efficient material usage. Hollow shaft, almost same strength, much lighter, better strength to weight ratio, widely used in automobiles and aircraft. In industry, hollow shafts are often the smarter choice. Shafts usually fail due to excessive shear stress, fatigue loading, sudden overload, poor material selection. Failure surface is typically at 45 degrees, which confirms maximum shear stress theory. Let's connect theory to practice. Gearbox shaft transmitting motor power, conveyor head shaft handling variable load, crane drum shaft under lifting torque, turbine shaft rotating at high speed. In all these cases, heavy checkmark torsional strength, heavy checkmark torsional stiffness, heavy checkmark fatigue life must be carefully checked. Let's quickly summarize. Torsion is twisting due to torque. Circular shafts are best for torsion. Shear stress is maximum at outer surface. Polar moment of inertia controls strength. Angle of twist controls stiffness. Hollow shafts are more efficient. Torsion equation links everything together. This topic is very important for strength of materials, frequently asked in GATE, SSCJE, PSU exams, extremely useful for design engineers, essential for maintenance and failure analysis. If you understand torsion well, you understand the backbone of rotating machinery. If you found this video helpful, please like, share, and subscribe to SimpleGAN. Comment below, backhand index pointing right, do you want a numerical problem video on torsion, backhand index pointing right, or a comparison video on hollow versus solid shafts? Until next time, keep learning, keep growing, and remember, engineering is simple when explained clearly. Thank you for watching.